Okay, you can repeat after. Sorry. Jorge is a PhD in computer science, um, and he works actually in grid computing group at BSC, and he has been involved in several national and European R&D projects. He has been a member of a program of committee of several international conferences and reviewer of journal articles. He also was a member of the Spanish National Grid Initiative panel, and currently is the research interests are focused in the energy efficiency, okay? In parallel programming models for heterogeneous parallel distributed computing environments and the semantic interoperability between the distributed computing platforms. Okay, we are going to enjoying the talk. If you want to introduce the title and yourself for your name. Thank you very much.
Can you hear me? Well. Okay, so thank you very much for the introduction. So I'm very happy to do this keynote speech. I did some presentations about papers in previous conferences, but it's an honor for me to do this speech and to speak about the project that we have been working during these last 2 days. 2 years. And the idea, well, I was started in the research in 2005, more or less, and at this moment we were working in clusters and grid computing, but just at this time we were starting also to work with web services and virtualization and what it was named by as cloud computing. Also, during this time in cloud computing, it has been evolved to different paradigms. So we started with the infrastructure as a service paradigm, where basically they offer us a virtual machine when we can customize the operating system, runtime applications, or whatever that we want to do. Then there was another level of abstraction that was the platform as a service paradigm, that in this case, basically the developer only has to deal with the application and the function, and the cloud is managing not only the hardware, also the operating system and the runtime. And finally, recently it has appeared the function as a service paradigm, that what is the user only has to deal with implementing the functions, and the cloud provider will manage the rest of the application stack. And the idea of how it works is that a developer that is interacting with a function as a service offering, that normally it's also called as a serverless, and it registers the implementation of the function, and it is offered to the users of this function as a REST API or an endpoint, and the other users or other systems can invoke these functions using this endpoint. And this offering, what is managing is the creation of the virtual machines, the containers, and so on, to manage the executions of these functions in a transparent way for the users. So in another way, the e-science workflows has been evolving making them more complex. So they are now combining traditional HPC simulations, but also with HPDA, with data analytics, also that are executed in HPC, or machine learning algorithms that has to be integrated to create larger workflows that are solving more complex scientific problems. And this is increasing the complexity in all the phases, in the development, because we have to use several workflows, but also in the deployment, because you have to deploy not only one framework, you have to deal with several installations, and also in the execution you have to orchestrate different frameworks, not just one. And also what they are trying to achieve is the integration of the data sources to this to fit these workflows. And also these workflows are very large computations, and sometimes the structure of these workflows have to change dynamically according to previous results or some events that can happen during the execution. So they are not static as just a number of steps and so on. So the current approach that we have in the HPC environments is that, okay, I'm a user community and I get access to an HPC system, so my workflow developers have to manually install the things, and sometimes they have to contact system administrators because they need to run some things as a super user, and they cannot do it by themselves. And once they have done this manual deployment, they provide the instructions about how to access and execute the workflow to the users' communities. So if the access to this machine has finished and then you get access to another machine, you have to do again the same, but customizing your workflow for this other system, and also passing the new instructions to the user communities. And if you want to integrate with data sources, you have to also do it manually in the cloud infrastructure or the repositories where you have the data. So what was our idea? It's, can we apply the same as we have commented about the function as a service in these complex workflows in HPC? So our idea is to provide more or less the same user model or execution model that the workflow developer has to develop the workflow in a way that we can pass to use what we have called HPC workflow as a service, that this will be managed by the workflow management stack, and it will deploy and execute the workflow in an automatic way for the users. So, and at the same time, once I have registered and deployed the service, I can provide to the users an API that they can easily execute the workflow as they are invoking a REST API. And this is what we were thinking, and we can see that there are similarities and differences of what is called function as a service. The similarities that we want to achieve is that they have to be easy to use for the final user. We want to automate this deployment and execution. We want to also integrate data, the sources of the data, because when you execute a function, as it is an execution in the cloud, normally you have the inputs from another cloud storage, and you want to store in another repository, and the data is not kept in the place where you are executing. So the results are also the inputs are gathered from the data source repositories and uploaded at the end to other repositories. And we also want to use containers because it's an easy way to manage the software stack. But there are some different differences, that the restrictions in HPC infrastructures are very restricted. You cannot do as you want as in the clouds, that you have super user access in the virtual machines and so on. Deployments is more complex than what is a function as a service, because the function as a service normally it's that you implement a function in one of the runtimes that they offer, like a Python or Java or a language. And then in this case, you have several, as I mentioned. There are HPC simulations, data analytics, machine learning algorithms that you have to to running the whole workflow. And also the performance is important because you are using an HPC infrastructure, so you want to keep the performance that you had in the beginning, because if you try to get a container that you have created for some machine or laptop, and you try to bring to the HPC infrastructure, you will see that the performance is not the same as when you execute in the bare metal installation. So, and what the opportunity that we had is that in the Euro HPC, that is maybe you all of you already know that this is a joint undertaking between the European Commission and some of the EU member states, and the goal of this joint undertaking is to deploy world-class supercomputing systems in Europe, but not only procuring and deploying the supercomputers, but also developing the software environments to run large and complex applications in these systems. And the eFlows4HPC project was funded in this call, and we were starting 2 years ago. So what is the objective of eFlows4HPC? It's that we want to provide this workflow management software stack that makes easier the management of these complex workflows. So we have to be able to combine different frameworks. We want to have these reactive or dynamic workflows with automatic workflow steering, and we want to keep we want to manage the full life cycle of the not just the execution as some of the workflow managers that are existing. We also want to incorporate what we call the data logistics, that are the movements of the data and the deployment of the workflow. And to do this, as I presented before, we had this idea of the HPC workflow as a service to make a mechanism to make it easier the usage and reusage of the workflows in HPC systems. And we also have a work package that we have selected the kernels that we have in our applications to optimize to new architectures for this. And the validation of the project is through three pillars that are workflows that are representing some of the centers of excellence in the Euro HPC framework. So in the workflows that we are tackling are the ones that I'm going to present now. In the first pillar, what we are focusing is it's in the generating digital twins for manufacturing. And in this case, what they are combining is the execution of the simulation of the full order models of the engines that has Siemens. And they are trying to apply some, from the data that is generated from these full order models, they are trying to get, to apply some machine learning techniques to get a reduced order model of these trains, and then they are doing the training of the ROM in the HPC and validating this. And if this is a loop that if you need more data, so if the accuracy when you validate here it's required, then you have a loop that you generate more models and then recalculate the thing, and this is a workflow that is running in the HPC, and once we have the ROM, this model can be deployed or in the edge or in the cloud to be used by the system that is running in the industry. Another use case that we are tackling is the climate modeling. In this case, what we are proposing is that in these workflows, what they are running is a lot of simulations, but sometimes some of these simulations are not. When we start and if we can check the results that are preliminary during the computation, we can see that some of these executions are not giving us to a value, the value that we want. So they can be pruned for the members that we are evaluating. And this can be done periodically, and at the end we will just run the members that are giving us the results that we want to have. And also, once we have the results of the simulations, we can apply some data analytics and machine learning to detect or some features of the climate models, like the tropical cyclones or other statistical analysis that we can do also at the time that the members are calculated. So not waiting until the end of the execution. And finally, the third case that it's the urgent computing for natural hazards, is that when an earthquake is happening, currently what we have to do, it's generating a lot of the different possibilities of stations that can detect this earthquake are providing us information, and this information is used to calculate what will be the impact of an earthquake in the ground, if it's or in the sea, if that it will be a tsunami. So when we want to predict the impact, or well, in this case, estimate the intensity maps for an earthquake, or the weight and or the flooding of a region in the case of a tsunami, and it is calculated with doing a lot of simulations in the HPC system. So some of the techniques that we are doing is that we are trying to estimate some of these simulations with machine learning models that can provide us faster results, preliminary results, and then we can confirm with more HPC simulations. So it's a combination of machine learning with HPC. So these are the three cases that we are considering, and to manage them in the HPC system, what we have implemented is the software stack that we have different layers. One is the part of the programming workflow that we use, the Python programming model, a Tosca that is a standard for the development and data logistics. Then we have a layer where we have the API for the HPC workflow as a service, and a set of catalogs that provide us to store the information that we want to be able to reuse in other workflows, or also the descriptions to make the things automatically executed in deployed and executed during the execution, during the life cycle of the workflow. And the final layer is basically the components that we have to manage the workflow, the deployment, the execution, and also the data management. So basically they are deployed that we have some gateway services that are installed outside the HPC system, that are the ones that the developers and users interact to perform the API and manage the workflow from outside the HPC system. And then we have other components that are executed are deployed inside the HPC system, that are to manage the execution inside the HPC system, like what we call runtime components. So, and how we implement this workflow? We have three parts. One is what we have called the data logistic pipelines, that are the description of the data movements and some filtering, what you can do at transit of the data, that you program as Python functions. And these Python functions will have some input that are described in the data catalogs, and they will be stored in and managed by a service that is the data logistics service. Then we have the computational workflow, that what we have is the PyCom's programming model that I will explain a little bit later, but it's basically that from a Python script we are extracting a computational workflow. And finally, to join all the steps that we need to manage the workflow we have the Tosca description. That basically it's the different components, the topology of the different components and the relationships that we have between them. So once we have this description, we have a component that is a graphical user interface called Alien for Cloud that allows us to create these Tosca environments and to deploy to the HPC system. So, and once we have deployed, we have an execution API that given an endpoint that provided by the developer, the users can execute the workflow in the HPC system. And for the deployment and the workflow, we have component that is the GST orchestrator that is interpreting this Tosca description and providing a high-level orchestration of the workflow to executing the data logistics, the PyCom's workflow, and the creation of the images, and also and so on. So PyCom's it's our programming model in BSC that is basically providing the sequential programming for workflows, but we are detecting the data dependencies in this sequential program and execute in parallel. So basically, we provide to Python functions some annotations to identify what are the tasks, the main computational parts, and the directionality of the data used by these tasks. And at runtime, so we will have some kind of this kind of workflow that we have the main code that is a Python script, and some functions that we have the annotation. If there is no directionality, we just indicate that this is an input and the return is an output. And but if we want to express that this is something that we modify, we can annotate in this way. So and the idea is that this annotation code is interpreted by a conf runtime and create a data dependency graph and execute the tasks in the different computing infrastructures. So it is offering to the user, to the developers, the illusion that you have a very big shared memory and distributed in a distributed system, and you don't need to deal with the details of the computing platform. So and you also can, as you are using Python as a programming model, you can also program all the characteristics that you can get from a programming language. You can make exceptions. You can also, and these exceptions are managed in a parallel way. So you can create some events to dynamically adapt the execution to create this graph in different way depending on the results of the application, or if there is exceptions or so on. So finally, what we extended this programming model in eFlows was in a way to be able to integrate different computations in the same workflow. So this is more or less the idea that we have, that if you have an HPC simulation and then you want to pass this to a data analytics, you have to use the HPC software for the simulation and the data analytics software for this. And normally you will have some kind of output here, and you have to transform to the input of the new application. So normally you do this programming some code to perform these executions and transform the data and perform the new executions. And normally our goal in eFlows was to reduce the glue code that we have to do, to allow the user to do the functionality and not the integration, and also to be able to reuse these codes for executing the different parts. So what we proposed was to, okay, in PyCom's we have the Python functions as tasks. So if we want to include a new execution that is not a Python task, but a Python code, but it's a binary or an MPI execution or whatever, we can define a function that is a dummy function, and we can annotate this function with a description and the data transformation that we need to apply before executing, and we can include in the workflow just as a call of this function. So this will reduce the programmability that the user has to do to execute this. And this invocation description can be reused for another system. If you want to do the same HPC simulation in another workflow, you just need to copy the description. And in the data transformation, the same. If you have to apply the same transformation, you just need to call this data transformation in another system. So this is more or less how this looks like. So in the software catalog, we have this invocation description. We apply this in the Python code. And at the end, what we have in the computing infrastructure, the runtime converts this description to the real software invocation. So for the data transformations, we have something similar that we add the data. We have the codes of the data transformations that can be added in before the execution of a software. So in the workflow, what we will have is here. Well, and we have this workflow basically that we have load some parameters. Then we have several simulations, and then the results of these simulations we want to apply a randomized SVD execution. So we have the data that is provided by the simulations in columns, and we want to split and distribute the things for calculating the randomized SVD in a parallel way. So we have to do this transformation. So we put here the part for load, the blocks, and rechunking to this way. And what is doing the workflow is that before executing the randomized SVD, that is this part, we have this other, and these are the simulations. We have this part that is the loading and the rechunking tasks at the beginning. So the user that is providing this code don't need to add always this code in the middle. So the workflow is cleaner, and you can focus in the implementation of the functionality. So basically, we have to tell what is the data that we want to apply the data, and we have to specify the function and the parameters of this function. So then the other part, so when we want to deploy this workflow that we have implemented, what we want is to deploy in containers. So to avoid to have this interaction with the system administrators and so on. So, but the problem of containers in HPC is that if you try to do a container in a standard way, you will have a receipt, like a Docker file that you have the dev or RPM's installations, and these packages are generic compilations for an architecture. So we are not getting the processor optimizations. So the containers provide us a simple way for deployment and also a portable way if we use this. But the problem is that the performance will not be good if we try to do in an HPC system. Well, it depends the application, but normally if you try to do for HPC systems, you will see that the performance is low than So there is this trade-off between portability and performance. If we apply our architecture optimizations and so on, also when we use the MPI or GPUs, we have to have some compatibility between the version that is installed in the host and the version that you have in the container to get the maximum performance of the system and to access to the hardware from the containers. So what we propose is to change a little bit the way that we create the containers. So instead of using the packages, the dev or RPM packages, we want to use the HPC, some of the HPC builders like EasyBuild or Spark that allow us to specify what is the architecture of the target system. So we can create containers for a specific platform where we can specify what is the compiler that we have, the MPI version or the CUDA version that we have, and the specific optimizations for the processor that we have in this system. So we will generate containers for these systems. And we will see that, okay, this could be very tough to do if you do in a manual way, but we can see that this can be automated in this process can be also automated. And for doing this, what we have created is this container image creation service that, given a workflow that we want to create, the container and the description of the platform that we want to execute, we can create this container. So we get some the software requirements from the workflow registry. We know how this, for instance, this workflow is installed using the HPC Builder packages. And then what we create is in a multi-platform build tool like BuildX or other systems. You can create this container image that will be stored in a container registry to be downloaded or copied to the system. The idea is that if you have a system that has the same MPI versions or the same architecture, you don't need to recompile again. You only need to recompile if the architecture is different and so on. But this is done only once. You can, every time that you execute, you can reuse this system. And okay, this compiling all this stuff can take time, some hours to compile, but the thing is that if you try to compile also in the HPC, you will have some interactions that can take also more time than this. Okay, and you just run the system, and you don't need to do it manually. The system will perform the execution. And the same container can be, if you want to do for another system, you don't need to change the description. You just need to change the platform, and the system will create the container image for the new system. So the systems are less, the container images are less portable, but we can see in the experiments that we did with the applications, especially in the HPC applications that we had in the system, that doing a generic container, we had less performance. Depending on the application, if in this case it was just shared memory, for the MPI we get better performance. But the nice thing is that we are very close to the native compilation. So the things that we apply at compilation time, we are getting this thing. And finally, how we integrate all together, it's with the Tosca modelization. What we apply is, as I commented, the different components of the workflow are executed, and we have the abstract description of an HPC site that is used to feed the image creation, the PyComps job. So when we want to, this is the description, and when we want to deploy in a system, what is doing Alien for Cloud in the case of the deployment is generating the installation workflow and execute it in the HPC system. And when the end user wants to execute the workflow, it is executing through the REST API that is provided for this. And Jorge is generating from the Tosca description the workflow for executing the application in the deployed HPC site. And more or less, sorry. This is what I wanted to explain to you about eFlows4HPC. So just for the takeaway messages, it's in eFlows4HPC we are trying to apply this function as a service model for HPC, that we try to facilitate the accessibility to HPC systems, reduce the workflow management efforts, and also be able to manage complex workflows and the whole life cycle. Also enable the reusability of the workflows and their components, and also facilitating the deployment through the HPC-ready containers. So thank you very much for your attention. And if you have more, you want more information, you can contact me, or also visit the eFlows4HPC website to get more information. Okay.
And they work in this. Okay, and I'm it's a really incredible presentation. I like a lot because I work in this field. And my curiosity is about how you manage when you execute an external software. For example, in the climate, I suppose there is a climate model that needs a lot of inputs as boundary conditions, initial conditions, whatever. How you manage the time of staging data from where the data is stored or from the previous task and the next task to be executed.
So
because it's
yeah.
time consuming a lot. I mean,
we have, so in this case, what we have is you in Tosca you can differentiate what you execute in the at deployment time and what you execute in the execution time. So when we deploy a workflow, well, this is just a template of one workflow. If you want to customize this, you can, for instance, add here. We are just in the installation creating the image and also the image transfer. In the data, in the part of the modeling data, what we added is the big. So normally they have some big information that is about a mesh of a region or something like this. That this is always the same for all most of the executions. So they deploy this in the deployment time. And the boundary conditions are stored in some repository that you download when you execute. Normally the boundary conditions are smaller and they are just for one execution. And this is executing before running the PyCom's job. And when we are executing different parts inside a workflow, what we have what is managed is by PyComs. And what we are doing is this Python workflow that if they are executed in the same HPC system, we are just PyComs is managing the data movements between the different nodes. If you have one part that has to be executed in one workflow in one HPC environment and another part that you need to do in another HPC environment, what you will have is two PyComs workflows. And you will have another HPC site environment to define that you are going to use two HPC sites. And normally you will have another data pipeline to move the data from one HPC site to the other. So this is the case. We have the data pipelines that are describing the data movements, and the PyCom's jobs are the workflows between inside the HPC system. So. And the Tosca modelization, what is providing you is what have to be executed first, then later, or if you need to have a movement of data from one sub-workflow and another sub-workflow. Okay. Thank you. Yeah.
Yes. Very good presentation. I was wondering if there are any facilities for abstracting some kind of workflows. I mean, what you showed as an example is a pipeline, basically. So is there any way to represent linear dependencies like the ones in a pipeline without specifying all the parameters that we have to specify if we go step by step in your process? So just to model those that are the most common forms of workflows that you have in these systems.
So some problems that we have when we try to model some workflows in a static way is that it is difficult to specify when there are some events in the middle of the workflow. This is why we have these two ways to specify. The Tosca part is more the typical static part that you apply the different steps, and in the PyCom's job what we have is the part of the dynamic computation, so inside the HPC side. So the problem is that in this model, the Tosca is good for modeling a normal execution of a workflow and the deployment, because it was more thought for the deployment and just the life cycle model. But it is not good for for the dynamicity and the execution. And this is why we propose these two ways. One for the management of the life cycle, and then another one for the management of the computational workflow. And what we, okay, in our case, what we proposed here was more or less a description of the different software that we use in a way that it was tailored for PyComs, okay? But I think this can be also proposed to use some kind of a standard way to be able to also reuse for other workflow managers, and in a similar way that we are doing for PyComs. So this is more or less what we have to model the workflows. So I don't know if I answered your question. Or if not, we can discuss later. Okay.
This one main is on artificial intelligence models. In the particular, have you considered particular libraries in Python, or you can consider different libraries? This is just one.
Yeah.
The second is about the use of different models in the workflow. For example, have you a model selection for data analytics and for machine learning, for example? In particular, I can use bias and neural network, but I can also use a deep neural network and so on.
Yeah.
Thank you.
The thing is that in the platform, in the project, what we have is several tools for implementing neural networks, European tools, because it was for Euro HPC, and we had
we participate in this.
Yes. So, for instance, for data analytics, we support Parsoda to do these data analytics pipelines. We also, for neuronal networks, we have EDDL, that is from the University of Valencia, that is the result of another project. And we also have Ophidia for also data analytics. And we also use DSLib, that is another tool.
There are specific models.
Yes, and these tools are offering to do several models. So, for instance, EDDL is more for neuronal networks, and you can model different neuronal networks. And the idea is that you can include in your workflow or some kind of machine learning training that you can do with these tools. And what we do to integrate in the workflow is that we have a description for this machine learning software. That is what I have explained, how we can execute it in the workflow, and we have different data transformations for doing the transformations of the loading and rechunking or transposing the data to provide in the way that the next step is going to get. And this is what we envision to do, this integration. And so we have done the work for the tools that are inside the project, but you can also add a PyTorch thing here for another tool, and also integrate in the workflow. Sometimes some of these tools are also using PyTorch as dependency, so or other tools, scikit-learn or something. We use scikit-learn in the
TensorFlow
or TensorFlow or something like this. So this is the way that we integrate this software in the workflow. Okay.
Thank you very much. Okay, I want to thank again